In my last lecture, the volume versus pressure curve for this reversible isothermal and reversible adiabatic for the ideal gas have not been drawn properly. And whenever this P versus V curve, in this case of P versus V curve, this adiabatic curve is steeper than isothermal. But whenever this V is plotted against P, and there is for this expansion, it is seen that the isothermal curve is steeper than this adiabatic, and you can show this by means of this slope del V by del P for the case of isothermal process for ideal gas, and is greater than del V by then dV by dP for this isothermal process, reversible isothermal process is greater than dV by dP for this adiabatic process. For ideal gas, it could be shown mathematically as for the case of a PV diagram shown. So this is the correction I can say for the last lectures. So you can follow, when you are following this last lecture, you can also this correction you add up. Thank you again. Today in lecture 5, I shall discuss the enthalpy of the system, and also after that I shall try to find out the expressions of Cp minus Cv for different substances. And this enthalpy is very important or useful thermodynamic properties of this thermodynamic property of the system. And the enthalpy is defined as U plus PV. U plus PV. P the pressure of this system, P the volume of the system, U the internal energy of the system, H is the enthalpy. So this it is seen that U is the energy term and PV is also the energy term. So sum of the energy terms will give also the energy term, and so enthalpy is an energy term. Not only that, U, P, V, they are the state functions. So H is also the state function. But however, this U is intrinsic property of this system, but here PV when added, the external pressure and volume are also included with this internal energy. So it is the total energy or total heat content of this system. I can compare the internal energy and enthalpy parallelly in two columns. Say this is the entropy, this is the internal energy. This is the internal energy and given by U. And this U we know the U is originating from the motion of the constituent particles of this system, and this is called internal kinetic energy. I have already discussed. And also the interparticle interaction, and this is the internal potential energy. both the terms are exclusively or solely dependent on this system. It is the intrinsic property of the system. But here, this enthalpy giving this symbol H, and since H is equal to U plus PV, so H is the internal energy which is U plus this external energy this is a PV. So this is called the total heat content. Total heat content of the system. This one is more useful than this internal energy. Then second one, U is state function and extensive in nature. And U is a function of temperature and volume for a definite amount of this system or closed system, I can say. And here for this enthalpy, H is also a state function and extensive in nature. And this H is a function of generally expressed as T and P. Then third one, I can say this Q, heat given to the system, is equal to this du plus PdV. This is the heat supplied to the system. The system will do this mechanical work, and the rest of this Q will raise the internal energy of the system. So at a constant volume, QV is equal to du. Though we know that Q is path function, but under this condition of constant pressure, this Q becomes this state function, and this value of this QV is definite, and actually the internal energy increase or internal energy change of the system is measured by the amount of heat supplied to the system at a constant volume. This will be the internal energy increase. If we divide these two terms by dt, then QV divided by del T at a constant volume, this one equal to del U by del T at a constant volume, and for 1 mole of this substance, 1 mole of the substance, this one is CV, molar heat capacity at constant volume. So we can define CV equal to del U by del T at a constant volume. Here also this H3, H equal to U plus PV. or dH equal to du plus P dV plus V dP. But this term, according to this first law, is equal to Q plus V dP. So if at a constant pressure, if we keep this pressure of this system is constant pressure, then QP, this one equal to 0, and so QP equal to dH by dHP. So in this case also QP, or this heat change, is also the state function under this condition of constant pressure. Not only that, the increase in enthalpy of this system is measured by the amount of heat supplied to this system at a constant pressure. And so, dividing by dt again, Q by del T at a constant volume equal to del H by del T at constant pressure, and here it is constant pressure, and for 1 mole of the substance, 1 mole of the substance, this one equal to Cp, means constant pressure, molar heat capacity of that substance. So I can write this Cp equal to del H by del T at a constant pressure. In chemical reactions, where the large amount of heat is either absorbed or evolved, in that case, the heat of reaction at constant pressure, is identified as Qp equal to del H. And here also this Qv means heat change or heat of reaction at constant volume of this reaction is identified with del U. That will be dealt in thermochemistry. So we are getting this definitions of Cv and definitions of Cp, and so now I can write here also, including giving one problem. Then dU equal to Cv dt. But for n moles du equal to n Cv dt. So this, of course, this relation holds at constant volume. And in this case also similarly, I can write this dH equal to n Cp dt for n mole of the substance at a constant pressure, constant P. So by this use of these two relations, we can calculate the entropy change, calculate the energy change or enthalpy change if we know this Cv and Cp and the temperature change. Suppose one problem I can give you here. This problem, 2 moles of helium gas is heated at a constant volume from 27 degree centigrade to 37 degree centigrade. Calculate del U of the process and given CV equal to 12.46 CV in Joule mole inverse Kelvin inverse equal to 12.465 plus 2 into 10 to the power minus 3 T. This calculation we can do here. du equal to NCV dt at a constant volume. So integrating this du here u1 u2 equal to n and here cv dt t1 t2 or here u2 minus u1 equal to n, and the value of CV is 12.465 integration dt t1 to t2 and plus 2.2 into 10 to the power minus 3 integration t1 to t2 and dt and bracket close. Or left hand side del u change in internal energy equal to n 12.465 into t2 minus t1 plus 2 into 10 to the power minus 3 divided by 2, and here the t2 square minus t1 square bracket close, third bracket close. So putting the values here, it is the 2 mole and here 12.465 and in this case 310 minus 300 and plus 1 into 10 to the power minus 3 into 310 square minus 300 square and bracket close and Joule mole inverse. Kelvin will be cancelled. Here it is the Kelvin, our Kelvin inverse will be cancelled. So this will be equal to mole inverse also cancelled. So 2 into here 12.465 into 10 and plus 1 into 10 to the power minus 3 and this one 310 plus 300 into 310 minus 300 bracket close, and it will be the Joule. If we do the calculations here, it will be 261.5 joule. Similarly, one problem I can give here for the students to work at home. For silver problem, silver Cp in joule mole inverse Kelvin inverse equal to 23.43 plus 0.00628 T. Calculate del H if 1 mole of silver is heated from 27 degrees centigrade to the melting point, 961 degree centigrade under 1 atmosphere. And answer of this problem will be 26,382.5 joule. Now I like to find different expressions of Cp minus Cv. First I shall deduce the general expressions in terms of pressure, volume, temperature, and then I shall apply it for different substances like ideal gas, van der Waals gas, water at 4 degrees centigrade, and also general expressions for the substances in all states of aggregation. According to the definition, this Cp minus Cv already I have done del H by del T at a constant pressure minus del U by del T at a constant volume. We can convert this H in terms of U, or we can convert this U in terms of H. But for the attempt, I shall take it here, this del, here H equal to U plus PV, and this del T at constant pressure minus del U by del T at a constant volume. And this will give you this del U by del T at a constant pressure plus, here P is constant, so P into del V by del T at a constant pressure and minus del U by del T at a constant volume. These two are same for this ideal gas. As we all know, the internal energy does not depend on this pressure and volume for this ideal gas. But we like to find this or reduce these expressions in general. So these two to be replaced or could be related. So U is a function of a temperature and volume. So du equal to del U by del T at a constant volume into dt plus del U by del V at constant temperature into dV. Or I can write dividing by dt at constant pressure del U by del T, dividing by del T at constant pressure, this one equal to this, and here dt is cancelled, so del U by del T at constant volume, and this one plus del U by del V at a constant temperature, and del V by del T at a constant pressure. So you can see this one, this and this one, this value. So it could be taken as minus. So this is equal to this. So Cp minus Cv equal to, then putting this one, dV del V by del T at constant pressure, del V by del T at constant pressure will get common. So it will be P plus del U by del V at constant temperature and del V by del T at constant pressure common. So again, this is not a fruitful expressions, as we have no instrument to determine the change in internal energy or to determine or measure this internal energy of a system. So this is to be replaced, and then we can get a very Cp minus Cv in terms of this measurable quantities, pressure, volume, temperature, etc. So one thing is the thermodynamic equation of state. Thermodynamic equation of state, which has not already been discussed. After this second law, I shall derive this thermodynamic equation of state, and this one is P plus del U by del V at a constant temperature, and this one equal to T into del P divided by del T at a constant volume. So inserting this one, replacing this one by this, we get this T and del P by del T at a constant volume and into del V by del T at a constant pressure. So this is the best relation number 1. So Cp minus Cv of any substance is expressed in terms of temperature, pressure, volume, etc., which are measurable quantities. So if we consider now for ideal gas, whose equation is PV equal to RT for 1 mole. This is for 1 mole. So del P by del T at a constant volume equal to R by V, and del V divided by del T at a constant pressure, this will also be R by P. So inserting this one, Cp minus Cv equal to T into R by V into R by P. So this is equal to R square T and divided by PV, and PV again equal to RT, and so this is R. Similarly, if we do this, if we find this equation, find the expression of Cp minus Cv for this gas, for the gas obeying P into V minus B equal to RT, then also it could be easy to show Cp minus Cv equal to R. Then here I can write this equation 1. Cp minus Cv equal to T into del P divided by del P at a constant volume into del V by del P at constant pressure. This is a very important relation to find out the expression of Cp minus Cv for any substance. So if we consider third one, Cp minus Cv for water at a 4 degrees centigrade. We know that at a 4 degrees centigrade, density of water is maximum, and the density is equal to molar mass by molar volume. So when density is maximum, means molar volume is minimum. So whenever the V is minimum at a certain temperature, so del V by del T at a constant pressure equal to 0. This is the condition for maximum minima in differential calculus. So putting here del V by del T at constant pressure equal to 0, we shall get a Cp minus Cv equal to 0. Means at this, for water at this temperature, Cp equal to Cv. Then fourth one. For Van der Waals gas. Van der Waals gas, and the equation for the Van der Waals gas for 1 mole, A by P plus A by B square into P minus B equal to RT, where A and B, these two are the Van der Waals constants. A measures the intermolecular attractions and B measures the size of this molecule. R is the universal gas constant. So we can write this or P equal to RT by V minus B minus A by B square. So this first term, differentiating P with respect to T at constant volume, means del P by del T at a constant volume equal to T with respect to T1. So it will be R divided by V minus B, and this is constant. So it is easy. Then del V by del T at constant pressure, it is not so easy to find these expressions. For that, this equation we can fully multiply when PV minus PV plus A by V minus AB by V square equal to RT. This could be calculated only putting some assumptions and approximations to these expressions whenever we like to find this expression, this one. So here A and AB by V square is a very small term. A small, B small, and V is large. V square is more large, so very small, and can be neglected. This is the first approximation. Neglected. So it is PV minus PV plus A by V square equal to RT. Then differentiating V with respect to T, keeping P constant. So here it is P, del V by del T at a constant P, and this P is constant, V is constant, so this one equal to 0, and this one minus A by this is V, A by V. A by V is A by V square into del V by del T at a constant pressure equal to R. So naturally del V by del T at a constant pressure equal to R divided by P minus A by V square. So this one equal to R divided by P minus A by V square. Now putting here Cp minus Cv equal to T into R by V minus V into R divided by P minus A by V square. So this is equal to T, R square T numerator, and here V minus V, and in this case we can write P plus A by V square minus twice A by V square bracket close, or P plus A by V square, P plus A by V square we can write RT by V minus V. So this one is R square T and divided by V minus V, and here it is RT divided by V minus V and minus twice A by V square and bracket closed, and this one equal to again R square T and divided by V minus V, and in this case I can write RT by V minus V. So let us take this common, RT by V minus V. So in this case it is 1 and minus twice A into V minus V divided by RT V square bracket close. V minus V cancels, RT cancel, and so there remains here R numerator and denominator 1 minus. Again V is very much high in comparison to V in this correction term, and RT V square is very large one. This quantity is very small, so we can neglect V in comparison to V, and V, another V will cancels, then 1 minus 2A divided by RT by V. So this equation, further clarification, this Cp minus Cv equal to R, and here 1 minus twice A divided by RT V to the power minus 1. So this term is very small in comparison to 1. So 1 minus x to the power minus 1, when x is much less than 1, it could be written as 1 plus x. So here also R into 1 plus 2A divided by RTV, or we can write R plus twice A, R cancels, so it is TV. It is usual practice to write this expression in terms of these properties which are intensive in nature. Here V, though it is the volume of 1 mole of this gas or 1 mole of the substance, V to be replaced by RT by V using this ideal gas, and this is the some approximation, some approximations. So Cp minus Cv equal to R plus twice A P divided by R T square, here RT square. So you can see for this Van der Waals gas, Cp minus Cv, this expression is greater than R. So this is the expressions of this Cp minus Cv for van der Waals gas. Now I am coming another beautiful expressions which will be valid for any substance in any state of aggregation. We know this alpha is the thermal coefficient, and this one equal to 1 by V into del V by del T at constant pressure. Again, beta equal to the compressibility coefficient, and this coefficient is defined by minus 1 by V and del V by del P at a constant temperature. As if you increase this pressure, volume will decrease, and so this negative sign is here. So alpha by beta, if we consider this alpha by beta, then it will be minus and del V, 1 by V cancels, and del V by del T at a constant pressure, and divided by del V by del P at del V by del T at constant pressure, and del V by del P at a constant temperature. We can write minus del V by del T at a constant pressure into del P by del V at a constant temperature. But since V is a function of a temperature and pressure, using this cyclic rule, here P, here V, here T, we can write the V by T, del V by del T at a constant pressure into this del T by del P at a constant volume, and into del P by del V at constant temperature equal to minus 1. So these two del V by del T at a constant pressure into del P by del V at constant temperature equal to minus 1 by del T by del P at a constant volume. This one. So this we can write minus del P by del T at a constant volume. So if we put here, instead of this 2, we can write this one. Then alpha by beta becomes equal to del P by del T at a constant volume. Now I can put here again from this expression, del V by del T at a constant pressure equal to alpha V. So here del P by Cp minus Cp equal to T into, instead of this one I can write alpha by beta, and for this one I can write alpha into V. So this is equal to alpha square PV divided by beta. And this is the expression, very beautiful expression in terms of alpha and beta, by which we can find out this difference between the two molar bit capacities for any substance in any state of aggregations. Here alpha, here V it is to be remembered that it is the volume of 1 mole of the substance with the temperature. To illustrate this problem, these relations, I like to state one problem. This problem is that a student attempting to remember a certain formula comes up with Cp minus Cv equal to Pv alpha to the power n divided by beta to the power n, where m and n, these two are the integers whose value the student has forgotten. So use the dimensional considerations to find m and n. The answer will be m equal to 2, n equal to 1, and dimensional considerations means left hand side, right hand side. You will have to express the length and mass and the time. These are the left hand side, right hand side. You can express in terms of this LMT, and then you equate two equations you will get, and for solving these two equations, n equal to 2, n equal to 1 will be obtained. And if you like to consult this problem, then I can suggest one book, Thermodynamics, Principles and Applications by Dr. N.C. Day, publisher, New Center, Book Agency, Calcutta 7001009. So this is all about the details of this enthalpy and the expression of Cp and Cp minus Cv for the different cases. And now I like to thank you all who are watching this video. In my next class, I shall try to explain the amount of work done in different processes. Okay, thank you.